Hi, everyone. Could you please thumbs up if you can see the screen? Thank you, everyone. Welcome everybody to our UCLA Quantum Science info session. We are really happy that you could join us this morning to learn more about our program, and we are really excited to share more information with you. So my name is Haiyi Li, and I am the Student Service Advisor for MQST program. I would like to introduce Professor Richard Ross, who is our program director, and he will share more information about the curriculum, course information, and career preparation later.
Hello, good morning, everyone. Thanks for joining us.
Thank you, Professor. So if you have questions that come up while you are listening to this or at the end, please type them in the chat and you will get to those. We will get to those at the end of the Q&A session. Sorry. So first of all, welcome again, and we are accepting applications for fall 2023 right now until the deadline, which is March 15. Exceptional applications will be submitted by our early deadline, which is January 15, 2023, and will be considered for early admission decisions. So this is UCLA. One of the most iconic building is Royce Hall, and UCLA is a very beautiful campus. If you are admitted into the program, it is a very great place to go to school. UCLA is located in the Westwood Village, Los Angeles, which is one of the best places to live in California. Also very safe to live. So Westwood Village always have fun activities like movie premieres, and first Thursday every month, you would have a wonderful experience when you're studying at UCLA. So back to the MQST program, quantum science is a growing field in the last 5 to 10 years. A number of major companies have started investing in this area, like large company like IBM, Google, Microsoft, and Texan. So this program was created in 2022 in responses to the increasingly high demands from students who are seeking for a master's degree in quantum science from UCLA and prepare students for a career in the full range of field of quantum technology. Students in MQST program will learn and strengthen their knowledge of foundation of quantum mechanics, quantum computing, quantum information, and quantum devices. So this program will prepare you for both research and development in quantum technology, learning how to work in the laboratory with quantum optics, quantum sensing, and the materials. Learning quantum science in UCLA will also increase your job marketability. Quantum in action. The Quantum Computing Student Association, QCSA, is also named CQSE at UCLA, is a combined undergrad and graduate student group under the Center of Quantum Science and Engineering, focused on everything under the umbrella of quantum information science. This is also including quantum computing, sensors, and algorithm. CQSE is also organized a journal club, social events, and various other career building events focused on quantum science. So I would like to show you a quick video about how CQSE helping quantum science students in UCLA. Please let me know if you can hear the
The Center for Quantum Science and Engineering at UCLA consists of a diverse group of scientists who are interested in collaborating in research projects that will tackle the most challenging problems in the quantum science and technology area. We sit at the heart of one of the most dynamic cities in the world and in an area where the local industry could very well dominate the quantum technology landscape for years to come. Solid state qubits are a very important area here at UCLA, and we're very strong in that particular area. Kang Wang and his laboratory, for example, is investigating topological materials and the application of topological materials to making topological qubits.
My research expertise is in scientific computing, and I work with others on the problems, what I would consider to be the practical aspects of quantum science. And in particular, I create and develop the simulations that are used by those researchers who are actually designing and fabricating quantum devices.
My name is Clarissa Yellow. I'm an assistant professor of electrical engineering here at UCLA. Part of our research has to do with the study of spins in biological systems. I believe that with the right type of machine, one can control biological spins in the same way that one can control spins inside crystals. And if that's so, one can think about in the very far future, try to start influencing physiological processes via those spin degrees of freedom that exist at room temperature and inside the wet-hot conditions of a cell.
The California Nanosystems Institute is a research institute on the UCLA campus that is obviously focused on nanotechnology. They have world-class capabilities that our center expects to be able to take great advantage of.
California Nanosystems Institute is the ideal partners to help me try to start tweaking physiological responses in biological systems via the spin degrees of freedom of my expertise.
I'm Wes Campbell. I'm a physicist at UCLA. We are down in a lab that works on quantum computing using lasers and trapped atomic ions. What we're trying to do here is to replace the hardware that people use in more conventional approaches to quantum computing by developing a new qubit. So each of these glowing white dots on the screen here is an individual atom of barium. And the reason we can see them is because we have them glowing in the dark by shining lasers at them. And they're very far from anything else because they're levitated in the middle of a vacuum chamber. These are the qubits inside our quantum computer. Yeah, this project is a really good example of the way that an organization like the Center for Quantum Science and Engineering can help us to work together to find ways to do things that are more than the sum of the parts. So this is actually a collaborative experiment with another, one of my colleagues, Eric Hudson, who's also a physicist here at UCLA. And I don't think either one of us would have been able to do this on our own.
Photonic qubits allow you a way to do secure communications in large data scale warehouses and also long distances. There are some challenges in photonic qubits. The first one being we want to pack a lot of information in a photon. Second is how do we transmit over long distances? And how do we do it effectively, efficiently in a single photon environment? Being here at UCLA allows us much more capabilities that I anticipated before I even came here. Particularly, for example, there's a very large industry component to Los Angeles that we're able to work with.
Interest in quantum science and technology has just exploded over the last several years. There are now major efforts at big companies like Microsoft and IBM and Google. There are efforts at smaller companies like HRL Laboratories, IonQ, Rigetti. So the landscape has changed dramatically. And along with that change in the landscape has been a need for people to enter the workforce in this area.
My name is Catherine Erickson, and I work.
Okay, thanks for watching the video. Let's continue to our info session. So Challenge Institute of Quantum Computation is also called CIQC. This is an academic institution looking forward to foreseeing future challenges to the realization of quantum computing. So meeting this task through intensive collaborative research that crosses multiple disciplines, such as chemistry, computer science, engineering, mathematics, material science, and physics. And I encourage everyone who has the aforementioned background knowledge to apply for our program, and you will have the opportunity to join CIQC when you are admitted. So our faculty is also one of the draw of the program. UCLA has pioneer faculty in quantum science, physics, and computer science, and our students are learning from them every single day. Professor Richard Ross is our program director, also is the instructor of all the lab classes. He will talk about the curriculum sequence later. And Professor Eric Hudson and his Hudson lab. I listed Professor Hudson current experiment. Professor Wes Campbell is one of the experienced faculty. His research group is to focus on novel species and novel ways to control them to leverage the built-in quantumness of these molecules for higher performance in these applications. And these are the lab photos for Professor Hongwen Jiang. I also attached each professor's web link, so feel free to check out after our info session. For the application checklist, just go over the application checklist for any of you that's planning to apply for fall 2023. One of the things we need is your official academic record. So it is your transcripts. We don't need you to send us the transcripts in the mail right now. All we need is you to download it from your school website and just upload it to your application. So if we need the official one, you will be contacted later about this. And please include in transcript from every university you have gone to. I know that some students went to 2 years in one school and another 2 years for another school. So please include in the transcripts for both of the schools. And for international students, if you are going to study abroad in country where you do not have English as language of institution or language of daily everyday life, so you will need to submit your TOEFL or IELTS. It is up to you which one you would like to do. And if you are going to, if you have gone to the school in the US or UK or Australia for at least 2 years full time, then you can be waived from language test. Statement of purpose are requested to submit. We would like to know why you are interested into quantum science and what would you hope to do in the future. It is a good way for us to learn more about you. At least 3 recommendation letters. So these can be from your professors, or if you were doing an internship, or if you have been working. So you can have it from a supervisor. I recommend you to have at least from academic, and the rest you can be from either academic or internship or your job supervisor. Your resume and CV we are required. Please put in any internship, any working experience, and if you have any technical or programming skills, it is a great place to put as well. And there is an application fee, and this is the same as for all the program at UCLA. I also want to go over the application timeline and the admission process. So as you can see on your screen, you should submit the application before March 15, 2023, and then will be reviewed by admission committee. And if you are selected, you will receive notification from the MQST program saying that you have been recommended for admission. After that, the admitted student will receive an official letter from UCLA graduate division. So that we'll be having a link for you to accept our offer. And if you would like to accept our offer, you would submit the statement of intent to register. It's also called SIR, as well as your deposit. So once you do that, you are officially part of the new MQST 2023 to 2024 cohort. All the applications must be received by March 15, 2023. Admission decisions sent on or before will be sent on or before April 15, 2023. And also, exceptional applications submitted by our early deadline, January 15, 2023, will be considered for an early admission decision. So for the program requirements, the minimum units for graduate required is 36 units for MQST courses. There are 32 units for the major requirement classes and 4 units for elective class. And you will be taking the elective class in the spring quarter. And the capstone is also one of the program requirements. Students must complete the program with a GPA of 3.0 or higher. For the capstone project, so this class will occur during summer session and consist for a 9-week research experience. Student will either perform research in the group of UCLA professor, for example, the faculty members of the UCLA Center of Quantum Science and Engineering, or through an approved internship at QST-related company. We will have a resume info session when you get admitted into the program to kind of like guide you, give you some suggestions on how to revise your resume, and we will collect all students' resume by a resume workbook and send it to the company. So during the 10 weeks of this session, a student will be prepared and present their research and will be evaluated on an oral exam. So next, I would like to hand it over to Professor Richard Ross to talk more about the courses we have and the curriculum and the career preparation.
Okay, thank you, Hai. So the MQST curriculum has been in the works for about 3.5 years. And what we have settled on is a program that covers a wide range of sort of the information and coursework that will prepare you quite well for any type of work and possibly future graduate work in the area of quantum computing and quantum information science. We have 2 tracks of classes. The first track we call theory classes, and this is a special set of classes focusing on physics-based quantum information science. These 2 courses in the fall and winter, quantum computation and quantum information, are very much focused on sort of graduate level quantum mechanics and as they apply to the field of quantum information science. And the spring class is a special topics class covering physical realizations of qubit systems and devices. The second track of classes, called programming, teaches quantum information science from more of a computer science perspective. So we have 2 full courses in quantum programming and quantum algorithms that I'll discuss a little bit more afterwards. And then finally, every student gets to take within the program 1 elective course chosen from a wide range of classes across physics, chemistry, computer science, electrical engineering, and possibly others. And this gives the students the ability to sort of choose something, more along the lines of the kind of work you intend to do, whether it be hardware, more software oriented, fabrication of materials and devices, and so on. And finally, a unique feature of our program is a full year of teaching laboratory classes. This begins right away in the fall and continues through all 3 quarters. And I'll say a little bit more about the contents of those lab modules. This past year was our first cohort of students, and as we expected, the laboratory courses typically take up about half of the students' total amount of time working in the program. So again, this is a quite unique feature of our program compared to many others you might be looking at, where we're, focusing on developing, in addition to a strong background in the theory and applications of quantum computing, but introducing hands-on experience where you will learn both sort of the skills and techniques in laboratory science across sort of the wide range of things that people do in developing qubit systems, qubit devices, and qubit technologies. So next slide, please. So a little more detail about the courses. So the first set of courses, which is sort of physics-based quantum computing. The first class, Introduction to Quantum Computing, is a new class we developed and is essentially a sort of a new version of a graduate level quantum mechanics class, where rather than focusing on fairly traditional quantum mechanics taught at the graduate level, that moves through sort of the basics of quantum mechanics and then sort of on to sort of the detailed description of three-dimensional quantum systems like atoms and molecules, scattering theory, and so on. This course takes a slightly different approach where we teach graduate level quantum mechanics, beginning with, sort of at the same level, Hamiltonian descriptions of physical and quantum systems, but then rapidly moves into sort of the ways in which quantum mechanics is represented and used for doing quantum information science, in particular, the description of quantum devices, how measurements are done, and how this relates to quantum circuits and quantum algorithms eventually. The second class, Theory of Quantum Computing, focuses on sort of special topic details within the field. In particular, we'll focus very much on how noise and decoherence mechanisms in various types of physical systems interact with sort of the nice clean quantum systems that you want to use for qubits, measures of fidelity, and some more advanced topics concerning the entanglement, creation, and distribution in systems, touches on information theory, and then various other things, including quantum communication applications, and so on. The final course, Theory of Quantum Devices, is intended to give a survey of the 3, 4, or 5 most sort of prominent qubit systems, specifically superconducting qubits, atomic and molecular qubits, and semiconductor spin-based quantum qubits, and sometimes a few others. We will spend 2 to 3 weeks on each of these topics, uncovering the sort of the details of the physics of these various systems, the types of noise models they represent, and how it relates back to sort of the Hamiltonian description of quantum computing and how gate circuits are constructed from them. The second course, the computer science sequence, teaches quantum programming and algorithms from a more traditional perspective that you might be familiar with if you've done any work in this field so far. So we start with sort of a very more simplified description of the dynamics of two-level systems treated as matrix quantum mechanics. And then we work through, how we build up quantum circuits and algorithms from that, including, sort of basic quantum algorithms such as Grover, Deutsch-Jozsa, the elements that go into Shor, and how these are implemented in various programming languages and executed on existing quantum cloud hardwares. The second course, Quantum Algorithms, is meant to go deeper into sort of the construction of real quantum algorithms that are being applied these days to quantum chemistry applications. Machine learning and optimization problems are turning out to be sort of one of the more fruitful near-term applications. And so in this class, we will cover this together with, some sort of detailed topics about quantum complexity theory, how classical and quantum algorithms relate to each other, areas in which quantum algorithms are beginning to show advantage. And finally, as I mentioned, the elective courses allow you to choose something, more specifically related to the type of work you intend to go to for your career in this field. Next course, next slide, please. Okay. So let me just say, before I go into this, a little bit more about the laboratory classes, as you'll be spending most of your time in this. The first quarter lab class is focused entirely on quantum optics, and this is intended to sort of develop skills in an optics laboratory, including the development of systems of free space optics together with various fiber optics. You'll learn how to tune up interferometers on the bench. We have systems that allow us to generate Bell states of 2-photon systems, and then do various experiments with those, including sort of generation of random numbers using a quantum system, quantum key distribution protocols, and some of the more interesting basic tests of quantum theory that are integral to the use of quantum information science for technology. And this includes sort of the demonstration of Bell inequalities, various types of single and 2-photon scattering and interactions. In the second laboratory during the winter quarter, we'll be studying ensemble spin systems using nuclear magnetic resonance. So this is a very nice way to study sort of large macroscopic ensembles of spin systems and how you can manipulate these even at room temperature using all of the tools of sort of quantum gate-based computing. So this is preparing ground states of these systems, manipulating them using polygates to carry out various operations, and how readout mechanisms work. And finally, in the spring semester, we have sort of a number of laboratories that students may take, including device fabrication and processing, focused mostly on semiconductor materials, advanced microscopy to do cross-sectional analysis of the insides of quantum devices. We have some laboratories that allow our students to learn how to work with sort of modern instrumentation, how to set up a measurement system based on lock-in amplification, laser, sort of the use of lasers to manipulate systems together with RF control, and a handful of other things. So let me go on to this slide, career preparation. So the Master of Quantum Science Technology program, MQST as we like to call it, is really tailor designed to train people that want to go off and work as quantum engineers in industry. The program provides a very nice balance of theories, applications, and hands-on skills. And this is motivated by sort of, my background coming from industry and a number of our colleagues who work at many of the major quantum hardware companies, where in the coming years, the workforce is going to require, many people beyond just people with PhDs. And so our program is focused on sort of, developing the skills and background of students with bachelor's degrees in physical science fields who want to understand quantum information at the graduate level and then go immediately and work in the industry, as opposed to pursuing a research career where you would spend years doing a PhD and then going off in that direction. So as we both said many times, our curriculum is really based on our knowledge and contacts within the quantum industry. And these include a wide range of companies, including private industry, national laboratories, FFRDCs, and academic groups. And so in conclusion, sort of, the goal of our program is to, give a very intense, short-term, 1 full year program that will enable you to go and work in this industry with, a much stronger base of knowledge than you would coming straight out of a bachelor's, and ideally be a productive contributor and lead research and development groups in the industry from the beginning. Next slide, please. Okay, so that's kind of an overview of the program. I urge you to please visit our website, which is qst.ucla.edu, where you can find much more information about our curriculum. You can find much more information about the requirements for applying, the timelines, and how to procedurally apply to our program. So I think with that, I'll hand it back to Hai, and we would love to take your questions and discussion about anything else related to our program.
Yeah, thank you, Professor Richard. So I would like to stop share and leave it to you. If you have any questions, please type them on the chat or just unmute yourself and ask.
I have a question about international student financial aid for the program. I'm just wondering if you guys offer any like grad assistantship or financial aid through the program itself, or how it works. I'm from Australia, so.
So
do you want to answer that, Hai, or would you like me to?
I think we have the fellowship, but can you answer that question?
Sure. So the program has a number of sources of fellowship funding available. This will be offered to select students during the application process. And this is generally based on, these are really scholarships that we use to help students. These are not things you can directly apply for. This past year, and we're hoping to do this again this year, we have a few companies who were able to offer fellowships, and in one case, they were treated just like our scholarships and sort of offered to students sort of during the application process. We had one other fellowship from another company that had a secondary application that students submitted again during the application process for eligibility. And so we don't have sort of direct scholarships that can be applied for. It's important to note, and I think we discussed this a fair amount on the website directly, that this is structured as a professional degree program. And so unlike academic programs, it is not eligible for, sort of the full range of financial aid, but there are many sources of loans that can be applied for, and our graduate division provides a significant amount of help for that. Regarding, international students, this past year, we did offer scholarships to a number of our international students in addition to U.S. students. We don't treat them separately.
Awesome. Thank you so much. That's very helpful.
Sure. Other questions?
Hi, Professor Ross. I am Manvi.
Hello, good morning.
Good morning. So I had a question that admission FAQ describes about the requirement of electricity and magnetism along with the quantum mechanics, right?
Yes.
So there it lists two books by Griffith's author, Introduction to Electrodynamics and Introduction to Quantum Mechanics. And there are a few chapters listed that we are basically expected to know. So would it be a good idea to basically go through those chapters and solve the numerical questions and the examples and basically maybe upload them somewhere, probably on GitHub, so that you can get a fair idea of our abilities?
Actually, that's an interesting idea. I had not thought of that. So, you know, this requirement is based on the fact that in particular, the physics track, the physics-based quantum information track courses and the laboratory courses are really starting in at this sort of senior undergraduate, first year graduate level for, you know, for physics science graduate students. And so, you know, having courses in both of these topics, not at the, you know, at the upper division, what we call the upper division undergraduate level, is really, you know, extremely helpful. And students that don't have that background at all would find it fairly challenging. And so doing sort of learning this material beforehand, ideally in a formal way through courses would be best. But, you know, in terms of sort of demonstrating your, you know, your facility with these in some way would be helpful. We haven't done that by looking at actual coursework, but that is, I think that is something that that we could consider. You know, keep in mind that, you know, graduate programs typically accept, you know, we typically have, you know, a fair number of applications to go through. So we can't spend an enormous amount of time on each one. But in terms of sort of demonstrating, you know, sort of your mastery of this material in some way would be helpful for us in making admissions decisions.
Thank you, Professor.
You're welcome, Navi.
I have one more general question about, I guess, what it looks like in terms of the course load, because I would be considering playing Division I beach volleyball for UCLA as well. So I just wanted to ask about what that would look like and if it would be better to ask them about being a grad assistant rather than an athlete for this program.
Yeah. So the course load is fairly, you know, I would say it's fairly time intensive. This will vary by quarter. Our first quarter this year, you know, was, you know, I would say students spent a significant amount of time each week working on the two courses and the laboratories. So I think, you know, it probably more than 40 hours a week of time spent. You know, this sort of varies. We have some students who are working as teaching assistants. We have some other students that have been working part-time in some professors' laboratories, and we have 2 students this year who are continuing to work part-time in the jobs that they came from. And, you know, from what I've heard so far, you know, doing more than like 5 to 10 hours a week of other work, you know, was sort of the maximum that they could really do. It depends very much, you know, it sort of varies by student how much time they really need to spend, but, you know, it is a fairly intensive program so far.
Okay, cool. Thank you so much.
You're welcome.
Hi, Professor. So, yeah, thank you for showing up. And so I'd just like to know what is the typical number of the enrollment size of the program?
Yeah, so currently we have our first cohort of students that we admitted last year, and the cohort size is 24 students, and we expect next year for it to be comparable.
Okay, thank you.
You're welcome. So it looks like we have somebody new who just joined us.
Yes.
Yeah, so we can probably let you know. So Karavi, so we had about 20 minutes of presentation, and now we're doing questions and answers. This has been recorded, so you can go back and watch that. And most of the information we're providing is can be found on our website. But we'd be very happy to take any questions now about any of that from you.
I saw someone just unmute themselves. Yeah. Do you have any questions, Lynn?
Yeah. Thank you. Hi, good morning, everyone. Hi, Professor Richard. Good morning. I have a question. So, because currently I'm working as a senior software engineer in a company, but I'm really interested in the program, and I would like to know, can I take as a part-time student?
So the structure of the program is that we can't do this part-time. We're basing this on a cohort model, and students need to be here in person for both the courses, which are taught during the day, and more importantly, the laboratory classes, where you need to be here a fair amount of the time. So there's currently no way to do this program part-time, we've had many questions over the years of people wanting to know if they can do this, part-time over 2 years, and the answer is currently we are not set up to do it that way.
Gotcha. Yeah, good to know. Thank you.
You're welcome. I think we did a good job explaining everything. If no one has any more questions. I guess we could ask the people here what they're looking for in a program, and if you are or are not seeing that in our program description.
Personally, for me, I really like that it's a condensed into 1 year versus the 2 years. I really appreciate that, can kind of get in and really focus on it, and then continue working. So that's definitely exciting, and yeah.
Yeah, we had a number of students that chose us specifically for that reason.
Hello. Oh.
You go first. Sorry.
No, sorry. I thought I cut you off. Sorry. Please go ahead.
Yeah, I just I just interested in the like a job opportunity after we finish these courses, and I would like to know more information about that.
So job opportunities in the field, what, yeah, let me, if you could just elaborate a tiny bit.
Yeah, I mean the job opportunity on the field after we finish those courses, and we want to look for a job related to our program.
Yeah. So so let's see. So over the past month, I've actually been to I think 4 different meetings of various types hosted by quantum industry, by the government, and an economic development group. And sort of, at this time, the number of job openings in quantum information, quantum computing, quantum technology development, there are an enormous number of job openings, and every employer reports that there are simply not enough qualified candidates to fill those jobs. These jobs represent a fairly wide range of things that are being looked for. So this includes, PhD sort of research scientists looking to work in quantum companies. This includes, sort of highly trained technicians in, mechanical engineering, electrical engineering, cryogenics, things like this. People with bachelor's or master's students background who have, sort of some knowledge of quantum information, and some that have a lot of knowledge of quantum information, to work in quantum software teams, to work in quantum hardware development teams, and so on. So as you look for academic programs, sort of to, give you a better training for one or another of these fields, it's sort of important to keep in mind that there's a fairly wide range of things that are being looked for. Our program is specifically targeted at developing sort of people with a very strong background in quantum information and quantum computing. And so, can be, after acclimating into a new job, be, sort of leaders of small groups of people working on mostly hardware development projects. So, as you can see, the lab, sort of the strong emphasis on laboratory work here is that our curriculum currently is, really focusing on people that want to work either directly with hardware or working sort of, close to hardware development teams. And this definitely includes, software, but, more specifically, the software that, sort of communicates with the systems, translates, sort of higher level descriptions of quantum circuits and algorithms into how would you realize this on hardware. And so we've chose a sort of a narrower focus than the field in general. There are definitely quantum companies that are looking for, true, just full-on software engineers. It sounds like that's what you've been working in. And in most cases, people with no background in quantum information who are software engineers find it difficult to come up to speed in a company that is doing software development for quantum systems. And so, so our program, will definitely provide, a lot of that background, and we have some students that are in that category. But so, other programs that are not as hardware focused, there are a variety of them out there these days. In some cases might be more appropriate for that. So, so keep in mind, as you look at all programs, what are they saying that, what sectors of the job markets are they looking for? As far as, I think what people really want to know is, if I take this program, will I get a job? And the answer is, like all academic programs. If you take this program, what I will say is you will be well prepared to apply for jobs and well prepared to sort of successfully procure one. As far as our program guaranteeing you a job, I think no academic program can possibly do that. But we believe that we will prepare people extremely well for the field, and we've been working in this. I've been working in quantum information for over 20 years, and have a fairly extensive network of people out in the industry that I know to help facilitate these interactions. So I hope that answers your question.
Yeah, sounds good. Yeah, thank you.
Thanks, Florence.
Hi, I had a question.
Yes.
Hi, so firstly, are there any integrated PhD programs along with the master's program, or is it just a standalone master's program in quantum technologies?
Yeah. So this is a standalone master's program. So this is intended to be a terminal master's program, and that means that there's no follow-on that you can go directly into. We actually have a number of students that are currently in the program and are applying for PhD programs because they've decided that they would like to give a try to sort of go that route. But yes, this is a terminal master's program.
I see. So I have a bachelor's in computer science. I majored in computer science for bachelor's, and then I have some research experience. So is a bachelor's in physics absolutely necessary, or will that greatly hamper my chances of getting into the program? The fact that I don't have a major in physics?
So the answer, so the real way to answer that question is you don't have to have a bachelor's degree in physics. It will be extremely helpful to have a decent amount of knowledge of undergraduate physical sciences. So you could have taken these courses in chemistry or in electrical engineering. So sometimes people who study computer science are also in an ECE department. If you have no background in physics at all, the program will likely be fairly challenging.
I see. Yeah, I do have some theoretical and experimental background, but just wanted to confirm if on paper a bachelor's degree in physics was an absolute requirement.
No, it is not. Yeah, it is not.
Right.
All right, so
Thank
there's a question in the chat. You're very welcome. So it says there's a requirement for bachelor's with an ABET accreditation. I believe that might be just a US thing. So 3-year bachelor degrees from European universities are absolutely appropriate training for this. You have to have completed a bachelor's degree in order to enter any graduate program at UCLA.
Yes, that's very helpful. Thank you so much.
You're welcome.
Hi, I have a quick question. So my question is that if we learn for the lab content, if we learn the software, the algorithm, based on the IBM their machine, so does it apply to the other Google and the other companies' machine?
I think you're asking if what's being taught can be used on other machines. Is that correct?
Yeah.
Yeah. So I mean, the answer is definitely yes. The only difference between running things on, you know, IBM systems or Google systems or IonQ or Quantinuum that have available platforms is sort of, you know, there are, you know, 3 or 4 sort of languages that, and each of them, you know, kind of has their own, although there's starting to be some, you know, sort of merging of these things. But, you know, everything we're teaching in the program applies to all of these, and it's simply a matter of sort of, you know, just rewriting them for you know, from Qiskit to Cirq, for example. So yeah, so everything that's taught in the program, nothing is really very specific to any particular hardware. You know, if you know, I know that Qiskit, you know, has an enormous amount of educational material available, where all of the examples are, you know, based in Qiskit, and there's definitely things in there that are very specific to IBM hardware. But for our program, you know, we're sort of teaching things at a level where they can be easily applied and translated into any of these. So I hope that answers your question.
Yeah, sounds great. Thank you.
Okay, well, looks like we're almost at time. So maybe if there's like one more question, we can take it.
Any last minute questions?
So maybe I have a quick question, yeah. So previously I have a PhD degree in maths major, but I'm not sure if I still am eligible to apply this master of quantum program because I want to shift my career. You know.
Yes, you can. Yeah, having you know, previous graduate degrees, no matter at what level, do not prevent you from applying to any other graduate program, at least at UCLA.
Okay, thank you.
You're welcome. Okay.
Okay. Again, thank you so much for attending our information session. And this session will be recorded and posted on our MQST website. And also you can find any information in our website. So thank you again for joining us.
Yeah. All right. Thank you, everyone. Have a wonderful holiday season and New Year, and we look forward to seeing your applications.
Thank you, everyone.
Thank you
So much.
Thank you.